Recall from pre-calculus that when you studied polynomial functions, and the chapter or the section was entitled Polynomial Functions, or it may have been entitled Zeros of Polynomial Functions. Basically, you were trying to find the x-intercepts of the graph. The graph might look something like this, and you were trying to find the spot where the graph crosses the x-axis. So you're looking for x-intercepts. And there were various techniques that we brought to bear on that. Well, in calculus, we can learn a great deal more about the behavior of the graph, not just the intercepts, but we can talk about things like what's the exact spot where we have the highest point along a certain interval here along the x-axis. What's the highest point in that interval, you see? And what's the highest point on the graph if it doesn't go off without bound over here? If it stops at a certain point over here, where's the highest point? If it stops right down here, is the highest point here or is it over here? We can tell that from calculus. We can tell things like what's the interval over which the graph has this kind of behavior, and exactly where does it start to turn back the other way? You know, that kind of thing is what we're going to be investigating. Well, the first several sections of this chapter are going to be more or less intuitive. It's going to be pretty much as we expect it to be. We're just going to talk about vocabulary, and that vocabulary will lead to almost an intuitive understanding of the situation from a calculus perspective. For example, here we're going to start with the idea of maximum and minimum. Now, our intuition tells us what maximum and minimum is all about. Maximum, a high point on the graph, minimum, a low point on the graph. And we're going to talk about maximum and minimum in terms of a certain interval, usually. Now, we may have the maximum and minimum for the entire graph if the graph is defined over a certain kind of interval. Well, we'll get to that in just a moment. The notion of maximum and minimum is the idea of extreme values. Extreme meaning maximum and minimum values, and the plural of extreme values would be extrema. So we're talking about extrema in this discussion. Now, a kind of a formal way of describing maximum and minimum would be like this. Let's suppose that we're given a function f on an interval I, and C is a point on that interval I. Then C is a maximum if f of C is greater than or equal to f of x for all x in that interval. You see, if f of C is greater than or equal to f of x. Now, look at what that means graphically. Now, along an interval, let's say this interval, along this interval, and we can see that point, the point right at the top of this peak, you see, is a maximum value, and it's x. It's f of some x here, and that x we're calling C. But for some C, f of C is bigger than f of any other x on the interval. And that's all that it's saying, and it's kind of an intuitive idea. And C is a minimum if f of C is less than or equal to f of x for all of the x's that are in that interval. Well, the notion of closed and open interval is going to play a role here. Let's think of a closed interval for the moment. There's a rather obvious theorem involving this idea of maximum and minimum, and it is this. It's called the extreme value theorem. If f is continuous on the closed interval AB, then f has both a max and a minimum on that closed interval. I mean, think about an interval A to B, and let's say that we've got a continuous graph now, and let's say these are the values at the ends of the interval. Now, I want to draw a graph between this point, which is f of A, and this point, which is f of B. I want to draw a graph between these 2 points. I want the graph to be continuous, and that just means that I can't lift the chalk off the board as I draw. I must draw this in such a way that there is a maximum and a minimum point. If I go this way or if I go down here, doesn't matter how I draw it, if I connect the 2 dots, you see, with a continuous curve, then I'm going to have a maximum and minimum value. And it turns out here that the maximum is here at this endpoint, the minimum is down here. But I do have a maximum and minimum. Now it's important that we have this closed interval idea. After all, if we have an open interval, look at what happens. Now the open interval simply means that I have no definition at these endpoints. So I would have something like this. Now in this circumstance, I have a minimum, but I have no maximum, you see, because there's no last point up here. The point right next to the one at the end is the one that would be the maximum, but gee, there's no last point that we can define. You tell me where you think that last point is, and I'll give you one in between the point you choose and that open spot right there on the graph. So it's important that for this to work, for us to have both a maximum and a minimum for a continuous function along an interval, the interval has to be closed. Now, sometimes there will be both a maximum and a minimum even if it's open, but we guarantee a max and a min if it's a closed interval and a continuous function. Let's look at a couple of other ideas. Consider this graph and this function along this interval from, let's say, this A and this B. Now, think about maximum and minimum both for the overall function on the interval and also within neighborhoods. Now, when I say within neighborhoods, I mean in this neighborhood there's a maximum point. You see, it's the top of this curve. And in this neighborhood there's a minimum point. It's the bottom of this part of the curve. So in a neighborhood we have relative maximum and minimum points on this graph. Now the overall, the absolute maximum within the entire interval is this endpoint. The absolute minimum is this endpoint. All right, so now when we start talking about maximums and minimums, we're thinking about situations within the interval. We're thinking about also the endpoints. So we have to take the endpoints into consideration along with situations in between those endpoints. Now think about the derivative of this function in this region. You see, in this region for that maximum point. What's the derivative of that function? Well, derivative is slope of the tangent line at a point. And if we're talking about the point being the top point right here on this curve, then the derivative, the slope of the tangent line, will be 0. And so it will be here for this lowest point. The derivative of the function will be 0. Slope of the tangent line will be 0. So really then we can find those relative maximum and minimum points by looking at the derivative, the zeros of the derivative function. And those values are called critical values. There are other critical values as well. Look at this one. Now here we have a situation where our maximum point is right up here at this peak. And when there's a sharp turn like this on a graph, we know that the derivative at that point, the derivative for this point, is going to be undefined. So we could have a maximum point at an undefined value within f prime. So if we examine f prime and we find the zeros of f prime and any places where f prime is undefined, then we have the potential for having maximum and minimum points on the graph. Relative maximum and minimums, or maybe absolute values, or absolute maximums and minimums for our graph. Here's an idea. Critical numbers. Critical numbers are values of f prime for which f prime is either 0 or undefined. Now they're critical because they are places where we're targeting as relative maximums or absolute maximums and minimums for a particular graph. Now we can say this, that relative maximum and minimum points occur only at critical numbers of f. You see, relative max and mins can occur only at those critical values, only at values where f prime is 0 or undefined. Now, it doesn't mean, though, that critical numbers always yield relative extremes. That is, just because you have a critical number doesn't mean that you absolutely have a max and minimum point. Let me give you an example. There's a possibility that a graph can come down like this, and then it can level off, and then it can continue to go down. You see at this point where it's kind of flat like this, the slope of the tangent line at a point right here is going to be 0. You see, and yet this is neither a max nor a min. It's not a relative max or a relative min. You see, so it's possible that we have a critical number that does not give us an extreme value. Here's the major task in this section. It is to find the extrema of some function. And let's find the extrema of this function on the interval from -1 to 2. Notice a closed interval now. And our concept here is to identify critical numbers by looking at the derivative and the zeros of the derivative and the undefined values for the derivative, and also examine those endpoints. So here's how we would proceed. Now, a lot of times a graph will help you to see what you might expect to happen in the calculations, and I've constructed the graph sort of here. Here's the left endpoint at -1 and the right endpoint at 2. And you can see that the maximum value is going to be at the right endpoint. And let's see, we're going to have a critical value here because the graph kind of flattens out. We have another critical value here because it's a low point, and it turns out to be the minimum. So we're looking for absolute max and min on this interval, and this will be the absolute minimum. There's the absolute maximum. So let's see how we calculate that algebraically. We begin by identifying critical numbers, and we do that by finding the derivative. Okay, so here's our function, and we find the derivative using the normal method, and f prime then of x is 12x cubed minus 12x squared. And now we want the zeros of this derivative function. That is, we set this expression equal to 0. It's kind of like y equals this expression. Let y be 0. You see, and we get the zeros of the rascal. So we'll factor here, and we yank out a common factor 12x squared, and the other factor is a binomial x minus 1. Now, the values of x that will cause each factor to become 0 are the zeros of the derivative. So the value of x that causes this part to be 0 is 0 itself. The value of x that causes this to be 0 is 1. So the zeros are x equals 0, x equals 1. These are the critical numbers. Now, with the critical numbers and the endpoints as our focus of our interest here, we're going to find f of the endpoints and f of the critical numbers. So we would proceed like this. We'd come over here and we'd say, okay, we have an endpoint. The left endpoint is at -1. So f of -1 means, in the f function, replace x with -1. So it would be 3 times -1 to the 4th minus 4 times -1 cubed, and it turns out to be 7. And then our first critical number, first meaning I'm kind of proceeding left to right. It doesn't matter the order in which you take these, though you don't have to proceed in some kind of order as I've done here. Just make sure you consider all of them. So one of the critical numbers is the 0. F of 0 would be, let's see, plug in the zeros here, and we find f of 0 to be 0. The other critical number was at 1. So f of 1 turns out to be, let's see, it's -1. And then the other endpoint was at 2, and f of 2 is 3 times 2 to the 4th minus 4 times 2 cubed, or 16. And now you just look around, and you're looking for maximums and minimums. So for the maximum, you're looking for the biggest number among these 4, and 16 is the biggest number, so 16 is the max. The max then is at that endpoint, the point 2, 16. And let's see, the minimum out of all of these, the smallest, -1. So this is the minimum, and the minimum then is at the point 1, -1, as we suspected from looking at the graph. Now, so that's the whole idea. You consider critical numbers, you consider endpoints, and you find the functional value at each of those, the value of the function at each of those points. It's also important for you to know that in finding critical values, you're not just looking for the zeros of the function, you're looking also at those values that would make the derivative function undefined. So, and we didn't have one of those here, but when you encounter one of those, that's a critical number as well. Here's one involving a trig function. It says find the extrema of f of x equals this on the interval from 0 to 2 pi, a rather familiar interval for us from trigonometry. Anyway, we begin by taking the derivative. Now notice I'm not saying we're going to begin by looking at a graph. Here, let's say that we don't have the luxury of constructing a graph very easily. On the previous problem, it was pretty easy to construct a little rudimentary graph because it was easy for us to plug in values of the left endpoint, and then I think, let's see, we started at -1, and I found f of 0 and f of 1 and f of 2, and I just made the graph. Okay, very easy. Here, it's a little more difficult to construct a graph, so I'm not bothering to do that. The concept, though, remains the same. What we're doing is we're considering the endpoints, but we also want the zeros or the undefined values for the derivative function. So we find the derivative function first, and now in finding the derivative function, let's see, the derivative here, it's 2 times the derivative of sine x is cosine x. And over here, I'm using the idea of the chain rule. And we have negative. We have the derivative of 2x is 2. So we have -2 times, let's see, the derivative of cosine 2x is negative sine x. So we have minus minus, which gives us plus, and it's 2 sine 2x. Okay, so here's our derivative function. Now we want the zeros of this. So we make this 0, and we want to solve this. And notice that what I've done, the trick here is right in this area. And I'm using the double angle identity, recall. Sine 2x is 2 sine x cosine x. It's a nice little replacement which allows us to create a factored form here. So with that replacement now, I'll take out, I'm noticing that cosine x appears as a factor here, cosine x is here, and I have a 2 here, and I'll snag out one of those other 2's. So 2 cosine x is factored as a common factor out of these 2 terms. When I take 2 cosine x out of this term, I'm left with 1. When I take 2 cosine x out of this term, I yank one of these 2's, and the cosine x, and what's left is 2 sine x. Okay, so I have this factored form. Now, I want the zeros, so I want the value of x that will cause this factor to be 0, and the value of x that causes this factor to be 0. Now, the value of x that will cause this factor to be 0 is a value of x that will cause cosine x to be 0. The cosine of what is 0? Well, you know, we don't have to resort to memorization for this. We can, I think it's important not to be bashful about going to a graph or some other kind of aid to help with this idea. You might try a triangle on a unit circle. You might be more familiar, or you might quickly think about the cosine curve. You think about a cosine curve like this. Gee, where along this curve is the cosine going to be 0? The cosine of what angle or how many radians would be 0? Well, let's see, it would occur right here. Here's pi. Oh, that's pi over 2. So the cosine of pi over 2 is 0. And we have another x-intercept for the cosine curve right here at 3 pi over 2. So for an x of pi over 2 or an x of 3 pi over 2, we have a 0 for this factor, and therefore a solution to this equation. So that's kind of the way we logically think our way through the problem. This part of it is a little more imposing. We're trying to find a value of x that will cause this factor to become 0. So we want to set this factor equal to 0 and solve it. Let's do that. And I've begun the process up here. So 0 is 1 plus 2 sine x, and then subtract 1 on both sides and we get this. Divide on both sides by 2 and we get this. Now we want to solve this, and basically it's saying the sine of what angle, or the sine of for how many radians would be -1/2. Now when I say what angle, a lot of times I think in angles in terms of degrees, but obviously angles can be thought of in terms of radian measure as well. We're gonna convert to radian measure, but I really don't know how you think about your sine and cosine values, and it doesn't make any difference. You need to go to a point of reference for yourself that's comfortable, and I want to encourage you to take your time with this. Don't depend on memorization. Don't expect that you should memorize everything about trigonometry to bring it to bear in problems like this. You can just use your fundamental concepts and build on those concepts and go through those concepts very quickly to arrive at a good result here. Let me show you how that might be done. Let's suppose you have forgotten values for the sign of what would give -1/2. Suppose you don't know. I might be inclined to forget that myself if I don't use it all the time. So what I could do is this. I might say, well, let me start with the sine curve. All right, in the sine curve, the sine of what value would give -1/2? Well, here's the sine curve. Now, where's -1/2? Well, that's right here. So I slide over, I've got a point right here and a point right here, such that the sine of that value is -1/2. Well, where is this? Gee, this is somewhat larger than pi, but it's before 3 pi over 2. Is it midway between these two? I don't think so. But at any rate, and we have another one over here. Well, let's see, where do we proceed? Gee, it might occur to us that this -1/2, ding, 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 clue phone, we might remember that this has something to do with the familiar 30-60 degree right triangle. You know, well, gee, I'm going to revert over to the idea of degree measure for a moment. Maybe that's the basis upon which we can build our logical pattern. So we might think, oh, well, let me just sketch something over here. I'm going to sketch, I don't recall whether it was sine or cosine, so I'll think in terms of the 30-60 degree right triangle, and you recall it was 1, 2, the square root of 3. Now, I'm talking about sine giving 1/2. The sine of which of these is 1/2? Well, it's the sine of the 30-degree angle opposite over hypotenuse. All right, that's the 1/2. Now, so I know I'm talking about a 30-degree angle, but the problem now is, what about the negative idea? Well, if I'm talking about reference angles of 30 degrees, and I think about, see, now I can jump over to the idea of a coordinate system. And I'm thinking then about, you know, the sine values in a coordinate plane. I'm thinking about angles that are within the coordinate plane, and I know that I have positive, the sine is positive in the first two quadrants and negative in these two. So I'm thinking about then a reference angle of 30 degrees, you see, in the third quadrant, and a reference angle of 30 degrees in the fourth quadrant. Well, how big are these angles? Well, let's see, this is 180 plus 30, oh, that's 210. All right, so now if that's a 210 degree angle, how do I change that to radians? You see, so you're just plotting through this and thinking logically through with information that you are familiar with if some of this stuff is not easily recalled. And I wouldn't expect it to be easily recalled at this point. All right, so we're talking about a 210 degree angle, and here's one of, let's see, 360 minus 30, that's 330. So we want to change this angle of 210 and 330 into radian measure. Well, recall that we can do that rather easily from trigonometry. It was theta in radians corresponds to pi in radians in the same way as theta in degrees corresponds to 180 degrees. You see, that was our fundamental idea of changing from radian measure to degree measure. That is a way of doing it, not the only way to do it. But at any rate, we have an angle here of 210 in degrees. So theta in radians compares to pi as 210 compares to 180. And now the zeros go out, and we think of a cancellation opportunity here. 3 into 21, 7. 3 into 18 goes 6. So we have 7 over 6. Now the pi, I'll multiply on both sides by pi, so we find theta to be 7 pi over 6. Now, in a similar way, and that's one of the solutions to this. So x then, our x here, is 7 pi, is 7 pi over 6. And going through the same process, we find that the other value is, I think it's 11, yes, it's 11 pi over 6. All right, so now we have 4 critical values. These are 2 of them. We found 2 of them a little earlier, plus we have the endpoints. Now we have to find f of the endpoints and f of the critical points. So we'll go over to the side and do that. Here's our left endpoint was at 0. So f of 0 I found to be -1. Now how did I find that? Well, here's how I did that. All right, come back over here and let's look at the function. I'm trying to find f of 0. So f of 0. Now sine of 0, now just recall the sine curve if you want to. The sine of 0 is 0. So 2 times 0 is 0. This goes out. And now the cosine of 2 times 0, 2 times 0 is 0. Cosine of 0, let's see, the cosine starts at the top of the amplitude, and so it's 1. So this turns out to be -1. So f of 0 is -1. So we come back over here and we pop that in. F of 0 is -1. Now let's think through. We'll think through one more of them, and I'll just give you the others. But think about f of pi over 2. All right, f of pi over 2. I'm saying here it's 3. Let's see why it's 3. We come back over here. We're thinking about pi over 2 and sine of pi over 2. Well, maybe we forget. Maybe we need to look at a sine curve for that. But the sine curve starts at 0, goes to the top of the amplitude and back to 0 at pi. And at pi over 2, then it's at the top of the amplitude or at 1. If you need a little aid with that, look over here. See, here's the sine curve. Here's 2 pi, here's pi. And at pi over 2, the sine curve is at 1. So the sine of pi over 2 is 1. 2 times 1 is 2. All right, this part is 2. And now cosine 2 times pi over 2. Imagine pi over 2, the 2's cancel, so this is cosine pi. So what's happening with the cosine curve right in the middle of the curve? Well, let's see. It goes like this. Here's the cosine curve right in the middle of the curve at pi. You see cosine of pi is -1. So back up here, this is -1. The negative of -1 is +1. So this is 2 plus 1 or 3. And that's how I arrived at the 3 over here. All right, then we do the same thing for the others. F of 7 pi over 6 turns out to be -3 over 2. F of 3 pi over 2 is -1. Then F of 11 pi over 6 is -3 over 2. And the other endpoint finally we get to is f of 2 pi is -1. Now we're looking at these functional values, and if we're trying to identify max and min, we're looking for both of the smallest and largest values for that function. So let's see, -1, -3 over 2. This is smaller than that is. So, or to the left of, less than, whatever. -3 over 2, all right? This is smaller than that is. Oh, here's another -3 over 2, and here's 3, and here's -1. All right, so the -3 over 2's are the same as one another, and they're the smallest values that we have here. So those are both minimums. So I'll put min for both of these. And the largest value we have in this group is 3. So 3 is the max. So we have one maximum value, two minimum values for this situation to identify the extremes. It might be helpful if we look at the graph of this situation just to verify what we just found out. I've already entered the function on the TI-83, and to select the window settings, remember we were talking about an interval from 0 to 2 pi, and I want to show you what happens on these calculators when you enter 2 pi. I entered this as 2 and then pi, which is a second function, and then when you cursor down, the 2 pi becomes some decimal equivalent. So that's why this is such a long decimal here, but I just entered it as 2 pi. Notice y minimum -4, y max 4, and here is the graph. We're looking for extrema, so we're looking for a maximum and minimum. And we're noticing from the graph right away that we have a single maximum up here and the possibility of two minimums down here. If we were looking at this without looking at the algebraic information that we had on the board earlier, we might think, well, gee, we don't know which one of these is a minimum or whether they are the same value. But at any rate, to make the calculation, we simply do this. We want this menu, that CALC menu, which is the second function on trace. So we press second trace. And now we cursor down. Now notice we have options for minimum and maximum. I'm going to press enter here with the maximum, and it is prompting us to select a left bound. You see that the calculator wants to calculate a maximum within a certain interval. So we want the left bound of the interval. Now we might say, well, gee, we want the interval from 0 to 2 pi, and we could certainly enter that idea if we cursor over to the left, the extreme left-hand side of our graph and go to the extreme right-hand side of the graph. But at any rate, I'm just going to get over to this side somewhere and press enter. And you know, since we have the value of, or the we have the graph on board and we can see the graph, then we certainly know that we are within the interval right here. We don't need to be really close to that maximum value. We can be in a very loose neighborhood, but I'm pressing enter here for a right bound, and now it's asking us for a guess. Now the guess for the calculator is just something, a value that the calculator can start its algorithm with. You see, and it will make the calculation regardless of where we choose that value, as far as I know. But the maximum is at an x of 1.57 and so on, and the y component is 3. And the y value of 3 is what we're looking for. That's what we found earlier algebraically. So we're just verifying that here. Now, in a similar way, we can press the right arrow key, and that's why this cursor is, you know, the icon is going over here. But we would find the minimum in the similar way. Second trace would give us the calculate menu, and then we're looking for a minimum, and then we'll cursor over, and anywhere we choose to, we can select a left bound. I'm going to choose to select it here, and then I'll go over and select a right bound. I know that within this interval we have a relative minimum point, and so I'll just go enter. And then for a guess, I'll just press enter again. Let's see what the calculator has to say. Notice the y value is -1.5, as we calculated earlier. We calculated this to be -3/2 or -1.5. And it is also giving us the x component here for that minimum. Now we want to verify or determine whether or not the minimum to the right of this is the same. And so we would go over and select minimum again, and then cursor over and get in the neighborhood of the other minimum value and press enter. And now we want the right bound. So we just want to go past that low point somewhere like this. I'll press enter, and then for a guess, I'll just use this point, entering again. And notice that the y component is again -1 1/2, and it also gives us the x component for that. Well, let's do this a little bit differently. I'm going to go to a home screen here by quitting out of this menu. It turns out that we can make the calculation using, well, through a more algebraic kind of approach. And we use the math menu. Within the math menu, I'm pressing the button marked math now. And within this within this menu, we have F-min and F-max. I'm going to press enter here for F-max, and the protocol is for us to enter our expression. Now the expression is kind of complicated this time. It's the expression that we've already entered as y1. So instead of entering this as 2 sine x minus cosine 2x, I think I'd like to just enter this as y1. So I'm pressing vars, and now I want a y variable. So I'm pressing the right arrow key. And now I want function, and it's y1 that I want. And now, comma, and I need the variable involved, and so I press in an x. And now it is requesting that I give it a lower bound and upper bound. And so I go 0 for the lower bound, and then for the upper bound I'll go 2 pi. So it's just 2 and then pi, close parenthesis, and bango. I pressed enter. Now it's calculating. Actually, it's calculating. Gee, this doesn't look like the maximum for us. The maximum was 3. Why is it 1.7? Well, this is the x component for that maximum. To get the y component, you see the y coordinate, then what we would have to do is take this x coordinate and evaluate y1 for this value of x. And actually, we can rather easily do that on the TI-83. We have to first save this value as x. So I want to store this number as x, and I simply press the STO button and X, and then enter. And so X has this value now. Now I want to evaluate Y1, so I go VARS, and then right arrow, enter, enter, enter. And there's the value for Y1 when X is 1.57 and so on. Well, the minimums work out the same way. The only trouble with dealing with minimums, and I'm going to go ahead and go through the calculation of it by going math, and then F-min is what I'm looking for, so that's item number 6. And then I want Y1, so it's VARS, right arrow, enter, enter, comma, the variable is X, and now I want lower and upper bounds. But the problem with this is that there are two minimums that have the same value, you see, and sometimes using this method you don't know that there are two of them. But if they are both equal to one another, then we know that we have at least one, we have the lowest value. It might also have another low value of the same size, but at any rate we get a minimum. We just don't know that we might have more than one. So let's see, 0 and then 2 pi again. And then here we go. Now once again, this is the X component for our minimum. And turns out to be the first X component from left to right. And so to find the Y component for this X value, we'll store as X, enter, and now we want to evaluate Y1. So it's VARS, right arrow, enter, 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 and -1.5 as we expected from before. Now, it turns out that using the TI-86, the situation is very much the same. That is, we'll go through this graphical thing, and we'll go through it a little faster this time with the TI-86. It looks almost identical to the one before. Now notice that I have already entered the function, and oh, incidentally, I don't want to get too far along here without mentioning, when I first entered this, the TI-86 doesn't automatically prompt the use of opening parenthesis after sine and cosine. I had to enter these myself, and without them the graph looked kind of funny. If you have a TI-86, you might experience that from time to time, so just be careful with the use of parenthesis on the TI-86. Anyway, the graph, I'm pressing second and then F5 to give us the graph. Graph looks as it did before. And we're going to go through the process of calculating max and min. The menus are just a little bit different, but they work out exactly the same way. That is, the menu for finding max and min is found this way. I'm going to press more, and then it's in the math menu, which is F1 here. And now notice that F4 and F5 are minimum and maximums. So it's the same idea as before. If I press F5, I'm prompted for a left bound. So I'll just go over here and I just want to end up somewhere to the left of this top point. Oh, let's say here. And now the right bound, I'll just go over to the right of that top point and enter. And now a guess, well, I'll use this point as a guess, so I'm pressing enter again. And it's giving me the coordinates, both coordinates now for that maximum point. And the same would be true for the minimum. We would go back into the math menu. I'm pressing graph now and more, and now math, and then we would select F minimum, and we would go through the same process. The algebraic method is also very much the same as the TI-83. I'm going to exit out of here. And the way to access the algebraic method is in the calc or calculate menu. It's second on the division sign, which is the calculation of items. Now we'll press more, and you see the F min and F max there. Let's do the F max for F2. And the protocol is the same as it was before. We want to enter the expression here. The expression is Y1, and we find Y1 in the catalog VARS menu, which is a second function on the custom button. And now, let's see, I'll press more, because it's not any of those items on the bottom. And it's an equation, so it's F4. And here's the only equation that we have defined, so I'll press enter, and there it is. So then, comma, the variable is x, and now we want lower and upper bound. So we press comma, 0 for the lower bound, comma, 2 pi for the upper bound, close parenthesis, enter. And as before, this is giving us the x component for that maximum. We want the y component for our purposes, so we'd like to store this as x and then evaluate y1. And y1 is found in the VARS menu, pressing More, and then Equation. We want F4, and then Enter, Enter. And there's the 3 that we expected.